Hello everyone, and welcome to my talk about improved distributed approximation for maximum weight independent set. This is a joint work with Kenichi Kawarabayashi, Aaron Schild, and Gregory Schwartzman. And I'm Seri. So before we start, let me just mention that the preliminary version of this work has appeared as a brief announcement in POTSI 2020, and there is even a 10-minute talk online as part of the POTSI program. And in this talk, we're going to dive into more details and provide the high-level idea of the analysis of our main result. So let's start. Given a graph, an independent set is a subset of the nodes where no two nodes in the subset are adjacent. And given a weighted graph where the weights are on the nodes, the maximum weight independent set is an independent set of maximum total weight. So in this example, the value of the maximum weight independent set is 20. The maximum weight independent set problem is known to be as one of the most fundamental problems in graph theory. And in the sequential setting, it's known to be an NP-hard problem. And even finding an approximation better than delta over log squared delta is hard, assuming the unique games conjecture, where delta is the maximum degree of a node in the graph. So throughout the talk, I'm going to denote by delta the maximum degree of the input graph. On the other hand, we know that very simple delta approximation algorithms are known even for the weighted case. And in this work, we were interested in the question, how fast can we find delta approximation to maximum weight independent set in the distributed setting? And why specifically we care about delta? Just because it seems to be the natural approximation factor to this problem, at least by looking at the situation from the sequential setting. Okay, so before we dive into the details of our work, let me just clarify what do we mean by approximation. So given an input graph G with set of nodes V, set of edges E, and a non-negative weight function W, and some positive number alpha, we say that an independent set I is alpha approximation to maximum weight independent set in G if the total weight of nodes in I is at least the total weight of nodes in the graph over alpha. So we denote by Wi the sum of weights of nodes in I, and we denote by Wv the sum of weights of nodes in B. So observe that this is slightly different than the standard definition for approximations. And this is because in the standard definition, we have here opt instead of Wv. But any independent set that is alpha approximation under this definition is also an alpha approximation under the standard definition. And this is because we can assume without loss of generality that W is a non-negative weight function. Because otherwise we can just throw the nodes with negative weights and they don't influence the value of the maximum weight independent set. Okay, so the plan for today is as follows. First, I'm going to tell you about the specific distributed model that we work with, which is the CONGEST model. Then I'm going to show you a very simple folklore ranking algorithm that already gives some nice approximation. Then I'm going to compare this algorithm to some related work and to our results. And then I'm going to show you the high-level idea of the proof of our main result, which is achieved by a technique that we call weighted sparsification. And first I'm going to show it for the unweighted case as a warm-up. And finally, I'm going to conclude with a summary and some open questions. So let's start with the CONGEST model. In the CONGEST model, we have a network of n nodes. Each node has an O of log n bit identifier. We have synchronized communication rounds. And in each round, each node can send an O of log n bit message to each of its neighbors. Okay? And we also assume that the nodes are computationally unbounded. And this is because we want to understand the pure challenges of communication. So we assume that any computation at any node can be done for free. So that's the CONGEST model. And the goal is in the CONGEST model is to compute some function of the network while minimizing the number of communication rounds. So the complexity measure is the number of rounds. Okay, so now let me tell you about a very simple folklore ranking algorithm for maximum weight independent set in the CONGEST model. So in this algorithm, we construct an independent set I as follows. We start by initiating I to be the empty set, and then each node V picks a random number Rv in the set of real numbers from 0 to 1. And we say that Rv is the rank of V. And then for any node V, if the rank of V is smaller than the ranks of the neighbors of V, then V joins the independent set. Okay, so that's how we construct the independent set I. For example, if our graph was a 4-cycle UVWZ, and U picks the rank 0.1, V picks the rank 0.4, W picks 0.3, and Z picks 0.2, then the two nodes that have ranks that are smaller than their neighbors are only U and Z, and they join the independent set. Okay, so that's the algorithm. Now let's see what is the quality of this algorithm. Does it give any good approximation? And it's not very hard to show that the expected weight of nodes in the independent set is at least a delta plus 1 approximation. And this is because the probability that a node V joins the independent set is 1 over the degree of V plus 1, which is at least 1 over delta plus 1. And this is because delta is the maximum degree of a node in the graph. So by using linearity of expectation, we can show that the expected weight of nodes in the independent set is at least the total weight of nodes in the graph over delta plus 1. And there is a work by Boppana, Halderson, and Ravitz in which they show a more sophisticated analysis to the same ranking algorithm that gives a slightly better approximation guarantee. And this algorithm can be implemented in a single round in the CONGEST model. And this is because you can show that instead of sending the entire real numbers, you can send only the first 5 log n positions after the point, and the analysis still works. Also the one by Boppana, Halderson, and Ravitz. Okay, so here we have an algorithm that can be implemented in a single round in the CONGEST model that gives an approximation even better than delta. So why do we even care about delta approximation in the CONGEST model? And the thing is that we can show that this algorithm doesn't give the expected guarantee with high probability. So we say that an algorithm works with high probability if it works with probability, say, 1 minus 1 over some poly n, or 1 minus 1 over n. And we can show that this algorithm cannot always give the expected guarantee with high probability. And for this, I want to show you the following counterexample. Okay, so we have here a graph, and the graph contains t clicks, C1, C2, up to Ct. All the clicks are of the same size, so the size of each Ci is n over t because we have n nodes in the graph, and here we have t clicks. And for any 2 adjacent clicks, we connect them by a biclick. Okay, where biclick means a full bipartite graph. So that's the construction. Now I want to show you that there is a non-negligible probability in which this algorithm doesn't return the expected guarantee on this construction. So let's see what is the expectation on this construction. And let's say that it's even unweighted, so the weight of all the nodes are just ones. Okay, so the expected weight of the independent set in this construction, or the expected size, because it's an unweighted graph, is t. And this is because the total weight of nodes in the graph is just the size of the graph, which is n, and the maximum degree of a node in this graph is something like n over t, or 3n over t. So the expected size of the independent set is something like t. And now I want to show you that there is an event that happens with non-negligible probability in which this algorithm returns only one node in the independent set in this construction. And here is the event. Let r star I be the minimum rank in the click Ci. Okay, so r star 1 is the minimum rank in the first click, r star 2 is the minimum rank in the second click, etc. And the event that I want to discuss is the event in which these ranks are monotonically increasing. So the smaller rank among these ranks is r star 1, the second one is r star 2, etc. And this event happens with probability 1 over t factorial. So if we pick t much smaller than log n, then this probability becomes much higher than 1 over n, or something like that. So if we pick t much smaller than log n, we get that this event happens with non-negligible probability. And if this event happens, then this algorithm returns only the node with rank r star 1 as the independent set. And this is because for any other node in the graph, it has at least one neighbor with a smaller rank. Okay, so that's the counter example. And in this work, we could show even a stronger theorem. So we could show that this example is not just a hard example for the ranking algorithm, but it's a hard example for any algorithm, even if the size of the messages is unbounded, which is well known as the local model. And the way that we show this omega of log star n lower bound on this construction is by reduction to Naor's lower bound for maximal independent set. So we show that if there is an algorithm that returns an O of delta approximation for maximum independent set on this construction, then this algorithm can be used to find the maximal independent set on a cycle with high probability. Okay, so now let me tell you about some related work that achieve approximation not only in expectation. Okay, so there is a work by Barry Huda, Sensor Hillel, Ghaffari, and Schwartzman, in which they show that the delta plus 1 approximation can be found in O of MIS log W round, where MIS is the time complexity of finding a maximal independent set, and W is the maximum weight of a node in the graph. Recall that the maximal independent set is not necessarily a maximum independent set or a maximum weight independent set. And whether this algorithm is deterministic or randomized that succeeds with high probability depends on the MIS algorithm that is run as a black box. Okay, and this time complexity translates to something like log delta times log n, and this is because W can be as large as poly n, and the time complexity of finding a maximal independent set is log delta plus poly log n round. Okay, and this is achieved by 3 works. The first is the recent breakthrough by Rozhon and Ghaffari, and another work by Ghaffari, and another work by Sensor Hillel, Parter, and Schwartzman. So the time complexity of finding a maximal independent set in the CONGEST model with high probability is O of log delta plus poly log n. And in this work, we show that by paying a multiplicative 1 plus epsilon factor in the approximation guarantee, we can achieve an exponential speedup compared to Barry Huda et al. And all I'm going to show you today is how to get an O of delta approximation in the same running time. So if you want to get a 1 plus epsilon delta approximation, then we need to use some more techniques. And unfortunately today I don't have much time to talk about these techniques, but if you are curious about these techniques, please feel free to contact either me or any of the authors. Okay, and today all I'm going to show you is how to get the O of delta approximation. Okay, so let me now talk about the main idea of our algorithm. And I'm going to start with a warm-up for the unweighted case, and then I'm going to explain how to extend it to the weighted case as well. So the first observation to make in unweighted graphs is that any maximal independent set contains at least n over delta plus 1 nodes. Okay, so by just finding a maximal independent set, we already find a delta plus 1 approximation for maximum independent set in unweighted graphs. And what is the runtime of finding a maximal independent set? So it's O of log delta plus poly log n. So if delta was small, let's say that delta was O of log n, then we would be done because we would get a poly log n time algorithm for delta plus 1 approximation in unweighted graphs. But unfortunately, delta can be as large as n. So the main idea is to sparsify the graph and to find the maximal independent set in a sparse subgraph H. And in order for this idea to work, we need to find the subgraph H with the following properties. First, the maximum degree in H is O of log n. And second, the ratio between the number of nodes in H to the maximum degree in H is at least as in G, or at least not very far from it. So if we find a subgraph H with these properties, then finding a maximal independent set in H returns an independent set of NH over delta H plus 1, which is omega of n over delta, which is an O of delta approximation for maximum independent set in the original input graph G. And because delta H is small, finding a maximal independent set in H takes only poly log n rounds. Okay? So now how can we find such a subgraph H with these two properties? And finding the subgraph H can be done via standard sampling argument in which each node joins H with probability log n over delta. And let's assume that delta is much larger than log n, otherwise we don't need to sparsify anything. Okay, and what we can prove is that if each node joins H with probability log n over delta, then these two properties hold with high probability by standard Chernoff and union bound arguments. Okay, so that's the whole idea for the unweighted case. In the weighted case, this approach runs into some challenges. And the first challenge is that a maximal independent set doesn't necessarily constitute a delta plus 1 approximation for maximum weight independent set. For example, in the following graph, this node of weight 1 is a maximal independent set, but it's very far from being a delta plus 1 approximation for maximum weight independent set. So the way we get around this in this work is as follows. We prove this theorem 1, in which we show that there is an algorithm A that finds an O of delta approximation in O of MIS time. So even though a maximal independent set doesn't necessarily constitute a delta plus 1 approximation for maximum weight independent set, there is an algorithm A that runs in O of MIS time that finds an O of delta approximation. So now, following this theorem 1, we're back to the starting point as in the unweighted case, because we have an algorithm that runs in O of log delta plus polylog log n rounds that finds an O of delta approximation. So if delta was small, let's say that delta was O of log n, then we would be done. But unfortunately, delta can be as large as n. So now we're going to use a similar sparsification technique, but we need to apply it for weighted graphs. So we need to find a subgraph H with slightly different properties compared to the properties that we needed for the unweighted case. And specifically, we need to find a subgraph H with the following properties. First, the maximum degree of H is small, as in the unweighted case, O of log n, so that we can find the maximal independent set in H fast. But now, instead of maintaining the ratio between the number of nodes in H to the maximum degree of H, we need to maintain the ratio between the total weight of nodes in H to the maximum degree in H. And we need this ratio to be at least as in G, or at least not very far from it. And if we can find such a sparse subgraph H, then we apply theorem 1 on H, which returns an O of delta H approximation in O of MIS time. And O of delta H approximation on H is also O of D approximation for the original input graph G, because of the second property. And finding maximal independent set in H takes O of log delta H plus polylog log n rounds, which is polylog log n rounds because delta H is small. Okay, so we need to find such a sparse subgraph H, and now the question is which sampling procedure we need to find this subgraph H. And the same sampling procedure from the unweighted case doesn't work, and there are counterexamples, but it turns out that it suffices to boost the sampling probability for a node V by a factor of the weight of V over the total weight of nodes in the graph. Okay, and by this boosting, we can show that we have a subgraph H with these two properties. And the way we prove it is as follows. The first property follows from standard Chernoff and union bound argument, so I'm not going to talk about that. The second property follows from Bernstein's inequality. Okay, so now WVH is not a sum of independent 0, 1 random variables, but it's a sum of independent weighted random variables, because we have weights on the nodes, because we are working in weighted graphs. Okay, so we're going to work with some weighted version of Chernoff, which is Bernstein. And let me tell you what is Bernstein's inequality. So Bernstein's inequality says that if we have a sum of independent random variables, such that each random variable is bounded from above by some parameter m, then for any positive t, it holds that the probability that the sum of random variables far from its expectation by an additive factor t is at most exponential in minus t squared over m plus the sum of variances. And don't think about this inequality too much for now. There are too many parameters here, and I don't expect you to remember it. But all I need you to observe is that if m, or the sum of variances, is large, then we don't get any good concentration from Bernstein. So the larger the m, or the larger the sum of the variances, the worse of a concentration we get from Bernstein. And this was one of the challenges in our concentration analysis. And let me tell you what we ended up doing eventually. So in our analysis, we look at the range of all possible weights, so from 0 to the maximum possible weight, and we fix some threshold which is WV over delta. And what we can show is that if most of the weight of nodes in the graph is distributed among lightweight nodes, which are nodes of weight maximum WV over delta, then we can use Bernstein's inequality to show a concentration bound. And this is because we can show that the maximum weight of a node in the subgraph induced by these nodes is at most WV over delta, which implies that also the sum of variances is small. And we can apply Bernstein to show a concentration bound. On the other hand, if most of the weight in the graph is distributed among heavyweight nodes, then intuitively all we need to show is that we pick enough of them. And when we say that all we need to show is that we pick enough of them, this is a sum of 0, 1 random variables, independent random variables. And this is because for any node, one knows if we picked it or if we didn't pick it. Okay? So for the other case, we are able to use Chernoff's bound to show a concentration. Okay, and that's the high-level idea of the case analysis to show our concentration. Okay, so that's all I wanted to tell you today. Let's summarize. So first, we think that it's interesting that the 1 plus epsilon delta approximation to maximum weight independent set can be found exponentially faster than finding a maximal independent set. And this is because a maximal independent set has this lower bound of omega of root of log n over log log n, shown by Kuhn, Moshe-Broda, and Waterhofer. And the algorithm that we showed in this work is randomized. And the natural question is whether we can find any deterministic algorithm in, say, sub-polylogarithmic number of rounds, say for O of delta approximation. And finally, our approach suffers from the fact that it can't give any approximation better than delta, because there are counterexamples for such sparsification techniques. And it would be nice to get any approximation better than delta in the CONGEST model. That's all I had for today. Thank you very much for listening, and see you in the online discussion.